Hello, everybody. I'm so thrilled to be here to get out again. I've already seen many people I haven't seen for many years, or 3 at least, or something, so it's a delight. I'm here to tell you about an experiment which has very, very high resolution, except on the electron-electric dipole moment. Obviously, I'm shamelessly taking advantage of how glamorous this picture is, but I'll try and make a connection, where I'm trying to measure the electron-electric dipole moment. And what we're looking at in this picture is many, many galaxies far away, about roughly 14 billion light years away, give or take. When we look at galaxies that are 14 billion light years away, the one thing that we do not see, we see all this light coming, but we don't see a huge flux of gamma rays, and that tells us that they're all made of matter or antimatter, one or the other, not both, otherwise we'd see the galaxies annihilating themselves. Galaxies have a core, but they have a diffuse cloud of gas around them that overlaps with that of other galaxies, and we don't see gamma rays coming from the spaces in between the galaxies either, and that tells us that galaxies which are 14 billion years away and 13.99 billion light years away, they're made of the same stuff, because we don't see galaxies coming in between them, so we don't see gamma rays coming from the space in between them, and so on, all the way down to our galaxy and our local stellar neighborhood. What this tells us is that whatever all the visible universe all the way down to our own planet must be made either of matter or antimatter, and we think it's matter as we describe it. All the way down to Detroit, Michigan and Windsor, Ontario, there's a free diffusion of people back and forth between Windsor and Detroit. They meet, they shake hands, they do not annihilate. And what tells us that even though for many ways the United States and Canada has mutually unintelligible social customs, all the same we're made of the same stuff. Okay, so from the ratio of photons to matter in the present universe, we can infer that once, back in the very early days, there was 1 part per billion more protons than antiprotons in the universe, and that very small difference grew to be 1 part per 1 when the universe expanded and cooled and all the protons and antiprotons recombined. So an important question is, where did this 1 part per billion time symmetry violating effect came from? It's an enormously important effect. It's why there's a universe at all, a universe that we would find interesting, a universe that we can exist in and have consciousness in and study it. And more to the point, where is this T-violating effect today? The standard model does not predict this much time symmetry violating stuff, and perhaps vestiges of it remained in the electron-electric dipole moment. This is one of the main motivations for looking for an electric dipole moment in the electron. I just wanted to mention sort of other ways of trying to look for exotic new particles include the Large Hadron Collider, where they smash 2 protons together at a center of mass energy of 14 TeV, and they smash together, and out in one direction you see all sorts of sort of boring particles, standard model dross, you might think of it, coming one way, and you have some missing momentum going in the other direction, and you'd like to associate that with a cool new particle. This very conceptually appealing picture of how people detect new particles is actually not how the Large Hadron Collider proposes to see new particles anymore. That was the original idea. They didn't see things that way. Instead, they're making, they're making very sensitive measurements, looking for anomalies in the standard model predicted cross sections. In other words, what they are doing is what they would call precision metrology on particle physics scattering, just like us ICAP people. They also are looking for new particles doing precision metrology. So it's no longer the case that there's a dichotomy between atomic physicists who look for new particle physics by looking at anomalies and accelerator physics people who look by new particles by seeing new particles. That era is over, and there are no more accelerators probably ever to be built. This is all that's left. So if you like particle physics, I hope you like this. This is what there's left anymore, probably forever. The electron-electric dipole moment, we're generously funded by many generous people. And here are some of the people who are involved in it. For many years, I've been doing this experiment jointly with Jun Yi. And then in the laboratory, we have 3 senior people, Tanya Rusi, Dr. Luke Caldwell, Qiaobun Ng, the senior people in the lab. I'll also mention Trevor Wright. The 3 people with asterisks there are all here at the conference. And I'll just call out Antonio Vigil, who is our superstar undergraduate, just recently got his summa cum laude undergraduate degree with us. And then the only other thing I'll mention about this picture is you'll note that Tanya Rusi, who's just 2 or 3 weeks short of being Dr. Tanya Rusi, owns a very heavy cotton shirt made of a bold red and black plaid. I think here in Ontario, we all know what that means. And also I mentioned that we had much useful collaborations with theorists, and particularly John Bone at the University of Colorado, but also theorists from around the world, Bob Field, Chris Green, and St. Petersburg Quantum Chemistry Group. What do I mean by the electric dipole moment? The electron is a small ball of charge, a monopole. It spins, which gives it a magnetic dipole, a north pole and a south pole. It's at least possible that in addition to this magnetic dipole, there's an electric dipole. Think of the north pole being slightly more positive charged than the south pole, or vice versa. We can think of the positive charge adding coherently or incoherently or destructively, and the negative charge adding constructively, so that an electric dipole moment in a charged particle just means that the center of charge and the center of mass are slightly offset from each other. So you think of these as in units of distance. And if it exists, sure, it violates time reversal symmetry and parity. What might be a natural scale for that length? Well, we know that an electron has a natural dipole scale. It's the dipole transition in a hydrogen atom or any charge 1 around any charge 1 particle, and that's the Bohr radius. When I was a child, we learned that electric and magnetic fields have the same units or same dimensions, which means that electric and magnetic dipole moments have the same units too, which is smaller than the Bohr radius by 1 factor of the fine structure constant. There's another natural length scale for the electron, which is we take 1 unit of charge and squeeze it together until the Coulomb energy classically is equal to the rest mass of the electron. That's called the classical radius. And that's smaller than the magnetic dipole by another factor of the fine structure constant. So we're down to about 3 femtometers. Another natural length scale, at least experimentally, is we could look for structure within the electron by scattering particles off each other at a very energetic accelerator. That's a little bit smaller yet. The current experimental limit from the ACME group is now 16 orders of magnitude smaller than any sort of natural length scale of the electron, and we're trying to go smaller yet. So what is significant about these 16 orders of magnitude? You can very generally make a Feynman diagram where an electron scatters off of a DC electric field and picks up an electric dipole moment, and there's meanwhile there's a single loop with some, but I made this slide back when there was supersymmetry, and so all particles start with S. But in any case, sort of generically, we anticipate that this effect will give rise to some electric dipole moment whose length scale is smaller than the classical radius by a factor which goes as the mass of the electron over the mass of some exotic new particle that gives rise to the symmetry violation. And with sort of natural assumptions, that sort of suggests that we're sensitive to things on the order of 10 TeV. And you should compare that with the last particle to be discovered in an accelerator, which was 0.1 TeV. So it's a sensitive, powerful way of looking for new physics. People have thought about this for a long time. They've been looking for new particles, or at least looking for the electron-electric dipole moment for a long time. Originally, it was done in atoms by the group at Amherst and by Eugene Cummins' group at Berkeley. Over the last 10 years or so, that gradually ran out of steam. Then was introduced the idea of using the natural enhancement of electric fields you can find inside a molecule, starting in the Imperial College group in London, the ACME group. The JILA group got into the business, my group, and June's group got into the business in the middle part of the last decade. And up through about 2017, we are nearly tied in an upper limit for the electron of about 10 to the minus 28. And those darn ACME people then did a factor of 10 better in 2018. We are very, very close to doing a new experiment, a better experiment. I really thought I was going to come to ICAP with a new measurement. And I'll explain to you, we're very, very close, but I'm not here to reveal a new measurement. The door's back there. There's coffee and cookies left over. However, we know that we don't know our number. We know the size of our error bars, which is about a factor of 2 smaller. That's coming in a month or so. How do you measure an electron-electric dipole moment? Much the same way as you would measure a magnetic dipole moment. You take a particle, spin up or spin down. If you want to see a magnetic moment, you put it in a magnetic field and you measure the resonance frequency for flipping it over. If you want to measure an electric dipole moment, you add an electric field and that would interact with any hypothetical electric dipole moment. You could do the experiment twice, once with the electric field parallel to and once with the electric field anti-parallel to the magnetic field. And that very small shift in the resonance then, you take a difference in those two resonance centers, the magnetic moment drops out, and what's left is just the electric dipole moment. If you want to do a really, really good electric dipole moment, you better have a really big electric field, you better have a long coherence time so your resonance lines are narrow, and you better have a large count rate so you can find the center of those resonance lines really precisely, and so you get a combined figure of merit. Big electric field, long coherence time, big count rate. It's hard to put together a large electric field and a large coherence time, because if you put an electron in a big electric field, it accelerates away. The standard approach is you take that electron and you stick it onto an atom, ideally a heavy Z atom, because there's a relativistic enhancement that Pat Sanders told us about. You stick your electron onto a large Z nucleus, and the atom inherits the electric dipole moment, inherits and actually magnifies the electric dipole moment of the electron through a relativistic effect, and you get a bigger effect. So that's one technique. We also get still bigger electric field by using a molecule. You can apply a much larger electric field inside a molecule than you can in free space. With a relatively small electric field in the laboratory on the order of 10 volts per centimeter, you can apply an electric field to the electron, an effective electric field, 9 orders of magnitude larger. The molecule is nature's way of amplifying electric fields to extremely high levels. Our approach to get a long coherence time is, instead of just using a molecule, we use a molecular ion. It's possible to trap neutral molecules, but it's still really hard. Many of you I know are trapping neutral molecules, and you know it's hard. After you've trapped a neutral molecule, you're tired. You don't want to do a precision metrology experiment. Trapping an ionic molecule is really easy. A measure of how easy it is I did it in the mid-1980s when I was a young graduate student. It's actually quite easy to trap ions, and we are doing that. So we're trapping ions our molecular ions in a trap. Problem with ion traps is that the electric fields are time varying, they're spatially inhomogeneous. How could you possibly do precision spectroscopy there? And to do that, we work with a particular kind of molecule, a molecule which has omega doubling. Basically, it has a non-zero projection of the electron's angular momentum along the intermolecular axis. That's called omega. Molecules like that come in, their eigenstates have come in states of good parity, which are superpositions of the molecule oriented along or against the electric field. You apply a relatively small electric field, you mix them, and you have states where the molecules are well oriented in space. And then you apply a magnetic field and you bias your levels that way. And then if your electron has a electric dipole moment, you can measure two different transitions, the transition between this state and the transition between these two states. And it turns out that the difference between those, the ambient magnetic field, the ambient electric field, everything drops out except for the electric dipole moment. At least we wish it were like that, and it's mostly like that. Certainly you get a an enormous suppression of systematic effects. Here is a lesson for everyone attending ICAP this year. This is a terrific idea, and I've been, along with Jun Yi, we've been working on implementing this particular idea for 15 years. But where did we come up with this idea? ICAP 2000. And not just ICAP, because we all know that we go to ICAP to get good ideas. I learned this idea in the poster session. I went to a poster session where I met for the first time this guy named Dave DeMille, who told me this really cool idea about how to do spectroscopy this way, how you could do precision spectroscopy using omega doublets. There's a lesson to be learned here, which is do not skip the poster session. That is where you're going to find your best ideas, and that's coming up soon. So how do you apply, we need to apply maybe not a very large electric bias field, but we have to apply an electric bias field of perhaps 10 volts per centimeter to polarize the molecule. And we're in an ion trap, and the point of an ion trap is that the ions are trapped in the place where the electric field vanishes. Because if the electric field didn't vanish there, the ion would move somewhere else to a place where it did vanish. So the way we do that is we want to polarize it, we want to polarize the molecule, but we have an ion, and so the molecule will fly away. So how do you do that? Well, we use a heavy ion storage ring. Here's one at Here's one in CERN. Basically, if you have an ion traveling around in a circle, you know that there must be an electric field always pointing inwards, so it will travel around a circle. There is an electric field. It's a relativistic electric field. Actually, there's a magnetic field pointing down into the Earth everywhere. The ion going around feels a relativistic electric field, which points inwards. So they feel a uniform electric field, except that it rotates in space. So that's what we do. We thought about building a relativistic ion collider here in Boulder. It would have gone right through the football field. We would have had to demolish the football field, which I saw as a plus with this idea. Not everyone felt the same way. In the end, we make a much smaller one. Basically, we don't have a ring at all. In our trap, we have a rotating electric bias field. It rotates rapidly enough that the ion doesn't go very far. It just traces out a small micromotion about 1 millimeter in diameter. So we have a 1 millimeter diameter heavy ion storage ring. But it goes slowly enough that the bias field, the molecular orientation has plenty of time to adiabatically track the rotating bias field, and we just do our spectroscopy in the rotating frame. It adds some additional terms that we have to keep track, but it's okay. We've got a lot of practice doing that. This is what our second generation experiment looks like. The distance between, this is a very, very large volume ion trap, so we can have very uniform fields. From here to here is about 8 centimeters. And maybe 15 centimeters end to end. Huge volume inside there. The ball of ions occupies about a cubic centimeter. And there's several tens of thousands of ions at any given time. We're using hafnium fluoride plus. We ablate some hafnium. We combine it with sulfur hexafluoride. We have neutral hafnium fluorine in a supersonic expansion. It travels along. It comes to the center of the trap. We ionize it. And as soon as it's ionized, it's easy to stop an ion. We apply a short pulse, just a few microseconds long, and the ion comes screaming to a stop. We turn on the trap. We use many, many lasers, literally about 10 lasers, to do state preparation and put all the spins, or as much as we can, all in exactly the same state. We apply a pi/2 pulse. The spins evolve for a little while. Another pi/2 pulse, classic Ramsey spectroscopy. And then to read out the spin, it'd be nice if we could do laser-induced fluorescence, but we have only a few hundreds of ions remaining in the desired state. And these are workhorse molecules. These aren't special molecules which have been selected to have high Frank-Condon overlaps. It's very hard to scatter. You can only scatter a few tens of photons off of this. So laser-induced fluorescence would not work. Instead, we use an action spectroscopy thing, contingent on whether the electron spin is pointing one direction or the other direction. It will absorb an additional photon and 2 more photons that will cause it to dissociate, to fly apart from hafnium fluoride plus into hafnium plus and neutral fluorine, or not, depending on the direction of the electron spin. So as we dissociate them with a laser, we kick them out of the trap, and they arrive on an ion detector quickly if they're light, like hafnium plus, or slowly if they're heavy, like hafnium fluoride plus. We have very, very good discrimination between these two species, and therefore very good discrimination between electron spin up and electron spin down in the molecule. I'm not going to go through the sequence of optical pumping. There's a lot of it. It's complicated. Come see me if you're interested in talking about it, or go to the poster session of Trevor Wright or Qiaobun Ng. There's 2 different posters about this, and you can learn all about it. But the short version is that when we're all done, we do Ramsey spectroscopy, and the y-axis here is basically how many of the ions arrive quickly because they're hafnium plus compared to how many of the ions arrive slowly because they're hafnium fluorine plus. And as that ratio oscillates, we are basically doing, probing the Ramsey spectroscopy of our fringes. And we take, roughly speaking, 1 sine wave worth at short time between 0 and 50 milliseconds, and another sine wave worth at late time, say 700 milliseconds. Now, actually, this is an old slide. Now we're up to about 2,000 milliseconds, 2 seconds of coherence time. And we fit this to a single continuous sine wave, or another way to think about it is we determine the 0 crossing of this little chunk of sine wave and the 0 crossing of this little chunk of sine wave, and the difference between them divided by the number of oscillations in between is just the frequency we're trying to measure. The experiment is mostly lasers. There's a whole room full of lasers. And then somewhere back in there, there's the ion trap I showed you about. We have collected, and this is why I was so optimistic I was bringing you a new result, about 600 hours of very high quality data. The statistical sensitivity is a tiny bit less than 2 times 10 to the minus 30 electron centimeters. The central value, we collected all this data with the central value blinded so as not to trick ourselves. We don't want to trick any of you, and we really don't want to trick ourselves. And we hope to unblind in a month or so and announce the result. So we think that the statistical sensitivity is very small. It's better than a factor of 2, smaller than the current limit. But how about the systematic errors? And I want to argue that we think they're pretty small, smaller than the other experiments around. And let me try and explain why we're so optimistic. When we do these experiments, okay, I've already said this. We look at Ramsey fringes, and we do it 2 different ways. One with the electron and the spin down, and with the molecule stretched one way, and one with the molecule stretched the other way. And we're taking a difference between the frequencies of these 2 different Ramsey fringes. So it's kind of the difference between this and this and this and this divided by that time gives us a signal. We actually do the experiment many different ways, with the magnetic field pointing one way, the other way, the electric field, the rotating, direction of rotation, and several other sort of state readout chops as well. Each time we do this, we collect a series of sine waves, and we combine all these different frequencies in a giant matrix with different linear combinations. One particular linear combination happens to be what we call the science signal, the one that's proportional to the electric dipole moment. The other ones tell us about various imperfections in the trap. So we can look at these different combinations and suss out all sorts of important things about what our systematic errors might be. Here's sort of a generic Ramsey experiment. You take your system, you prepare it so you have as many atoms as possible or molecules as possible in the spin down condition. You apply a pi/2 pulse, and the spin rotates up in the Bloch sphere. You wait a little while, and the spin processes around and around the equator. You apply a second pi/2 pulse, and then you measure what's left. Most of the systematic errors, most of the errors which are difficult to characterize, occur during the state preparation and Rabi pulse, pi/2 Rabi pulse, or during the second Rabi pulse of the state measurement. This is a relatively boring period of the experiment. I would say boring because it's very well controlled. So we can, with this first part, we can characterize a phase error, some sort of systematic error. With the second part, we can characterize a systematic error. We do a Ramsey experiment, and we measure some final phase, and that final phase is perturbed by the difference between those 2 systematic errors. And then that gets converted into an error in frequency, the slope, which is given by this, whatever these errors are, divided by the Ramsey time. And then that error in the slope gets converted into an electric dipole moment, dividing it by the effective electric field. The huge advantage we have over the other experiments is our product of Ramsey time and effective electric field is about 1,000 times larger than any other experiment. It means that we are 1,000 times less sensitive to errors in all these state preparation, state readout, and corresponding Ramsey time. You say 2 minutes? 3 minutes. Well, we'll zoom right along then. What I want to say then is that comparing old experiments, what we see is that in contrast to old experiments, for instance, the original Berkeley experiment, they had to make, in order to get their claimed sensitivity, which was not very good by current standards, good for the day, they had to keep their phase errors to under a microradian. The ACME 2 experiment had to keep their phase errors to under 1.5 microradians. We're able to keep our phase errors for our claimed precision to 240 microradians, almost a milliradian. This is child's play. If you can't make a measurement to a milliradian, you shouldn't be in precision spectroscopy. So we're relatively insensitive to these things. And I'll go further. We actually do the Ramsey things at short time and at narrow time. So even we do not have to assume that the phase is 0 here. We do it at early and late times by doing basically early time and late time Ramsey fringes, which you can't do in a beam. Hard to do in a fountain. You can only do this. What I want to say is that it's very, very difficult for us to impose an error large enough for us to see in the state preparation stuff. Are there still errors? Sure. The errors occur here when we don't have any laser beams, we don't have any microwaves, everything is uniform. The fields are governed not by imperfections in your wave plates or anything like that, not by materials, just by the fields in the center of your trap, which obey Maxwell's equations, and you have a small ball of ions inside a large set of electrodes. The fields are relatively easy to characterize in terms of a multipole expansion. It becomes a much more, I would say, sort of deterministic, easy to understand process. I'm not saying it's easy, I'm just saying it's easier to do a precision measurement this way. I'm short on time, so I'm going to jump through our other systematic errors associated with the boring part of the system. Boring and easy, but still not completely easy part of the systematic errors, where we look at Berry's phase, we look at inhomogeneities in the magnetic field, we look at second harmonics on the rotating electric field. All these things end up being important. And we get to a sensitivity of statistical, here's our data, statistical sensitivity, 2 × 10⁻30, small systematic errors. We anticipate coming in about a factor of 2 smaller. We're taking our data blind, but where are we at? Here is the ACME result, 4 ± 4 × 10⁻30. Traditionally, in this business, we like to express this as a symmetric thing. We say the absolute value of the electric field is less than, say, 11 × 10⁻30 at 90% confidence level. But you can see that it's actually, typically, it's not a particularly, you don't have a particularly symmetric result. So where are we going to come in? Our error bars are going to be about a factor of 2 smaller, but I don't know what the answer is. If it comes in here, we'll have correspondingly smaller limit. It would be nice if we had a really small central value, because then for the same amount of error, we'd have quite a bit smaller upper limits on the symmetric plus or minus size of the electric dipole moment. But as far as I'm concerned, it might come in there, but it could easily come in there. This value of 10 × 10⁻30 respects the ACME result for the upper limit. It's in reasonable qualitative agreement with their central value, and it would be 5 sigma away from 0. That would be exciting. Or, even more exciting, but in a different way, it could wind up over here. Again, 5 sigma away from 0, but in 3 sigma disagreement with ACME, which would be an uncomfortable place to be, because I have a lot of respect for those guys. We don't know. Trevor Wright is giving a poster about this. You can see all the details tomorrow night. We are actually going to do yet another factor of at least 5 better in a generation 3 machine. You can see a poster about that for Qiabun Ng. I don't have time to tell you about that experiment, but we have recently assembled it. This is Sun-Yul Park and Noah Schlossberg assembling the 3rd generation machine, and we have the signal for the first ions coming out of the 3rd generation machine already built, even though the 2nd generation is not fully complete. In June of 22, this is what they look like. Actually, that's what they look like. Just as beautiful as far as I'm concerned. We are very excited to see our first ions coming out of the experiment. Ask Qiabun Ng about it on Thursday, and that's all I have to tell you about.
Thank you so much, Eric. We'll start with a question, though. It's a question here. That's the first one I saw.
Thank you very much for a wonderful talk. I'm going to ask a nonsense question. So what I noticed is that if we have magnetic dipole, if we have spin and we have electric dipole of electron, and they have non-zero projection on each other, it means that electron becomes chiral. And I also noticed that you apply chiral field configuration, which is E dot B. So I was wondering, so now is complete science fiction. So suppose I would base my measurement on an anti-sensitive Stark shift, which is due to electric magnetic susceptibility, and the molecule which has this chiral electron will leave the trap if the electron is left, and not leave with that's the right electron. So something along these lines. I know it's a bit, I did not think it through, but.
You're suggesting that what if we use a chiral molecule?
That was another idea, but at that point I would say no, because the electron is chiral itself now, which means the molecule as a whole is going to show chiral properties.
Okay.
So, and which means that you will get an anti-sensitive Stark shift, and if you get fields E dot B, this is a pseudo-scalar.
Yeah.
So if you change sign of the pseudo-scalar, you should release your molecule or trap your molecule depending on your basically configuration.
You're talking about an additional force, which has to do with the ion field because of the chirality?
Yes, because you have a chiral field,
Yeah.
E dot B
Yeah.
makes pseudoscalar.
Yeah.
And if electron has electric moment, D dot spin also makes pseudoscalar.
Yeah.
And I'm assuming that I can use it's a linear process, and I can use the electric magnetic susceptibility, which would lead to additional enantiosensitive Stark shift,
Yeah.
and that will change the energy,
Yeah.
and therefore you can either release molecule or trap it more.
Yeah.
I understand that it's a small effect, but it's
Yeah.
still interesting if somebody thought about this kind of nonsense.
It's interesting because, the very first measurements of dipole moments were done using forces, right? They had a magnetic moment going along, it came to a magnetic field gradient, and it moved one way or another way. This is Stern-Gerlach, right? This is there is a very, very long, honorable tradition of using forces on molecules or on particles to see dipole moments, let's say. These days, the stakes are higher, the sensitivities are higher, the force would be very, very small. But I like that. I like the idea because it sort of harkens back to our roots, 1920s or something like that. It's very, very classical, very appealing. Yeah, thank you for that question.
Great. Other questions right here? And then Bill?
Thank you for this great talk. Maybe you skip the slides, but I'm really curious to know how hard it is to keep the amplitude of the electric field stable, and how hard it is to not maybe excite some center of mass motion of these molecules.
Yeah. We know that as for keeping the magnitude of the rotating electric field stable, longer-term drifts don't hurt us very much because the transition energy we see is very insensitive to the exact value of the electric field. So that's okay. What can cause us problem if there's little, frequency noise in the strength of the electric field, especially at frequencies which correspond to the center of mass motion. And where we have the biggest problem is that we have a room full of powerful lasers, and they fire 10 times a second. And every time they fire, everything in our lab gets a little electric burst on it, including the op amps whose job it is to apply electric fields to the electrodes. So in early versions of these experiments, we would see a lot of heating associated with the electron getting hotter and hotter in the trap exactly because of pickup from the noise of the lasers. And we had to do a lot of shielding and things like that. At this point, it's not too much of a problem. The thing that helps us is that the frequency of the electron sloshing in the trap is relatively high Q. It's a well-defined frequency. And so the noise on the op amps and so on is relatively broadband. And the part of that noise inside the bandwidth of the oscillating ion resonance is relatively small. So at least for a second or two, it doesn't heat up very much. Longer time, yeah, eventually we see the ions start to slosh around. Yeah, definitely.
Thank you.
Thanks. I saw Bill's hand up. Yeah. Here it comes.
So I have a mundane question. And
You have a question, Bill?
Well, I was trying to categorize it. I have a mundane one and a stupid one. So the mundane question is, what is it that limits the contrast of the Ramsey fringes? And the stupid question is, you gave us this image of what a dipole moment means, that the center of mass is different from the center of charge, but the size of an electron is 0. So how should I think of it in a slightly more mature way?
Okay. Wait, what was the first one, the mundane one?
That was what causes the contrast of the Ramsey fringes to be what it is.
The main thing that limits our Ramsey fringe contrast, Ramsey fringe contrast is off-diagonal Frank-Condon matrix for this particular molecule. This molecule was not picked for its ability to be laser cooled or optically pumped. So we can tinker with the duration of all the pulses, but the problem is not the purity of our polarization or anything like that. The problem is that we can only pump so long before they decay down into, so what you're seeing is a compromise between high contrast and high number. And this is sort of kind of where we could probably do a little better in contrast, but we start losing more. So that's all that is. Yeah. Longer term, that's the initial contrast. Longer term contrast decays due to ion-ion collisions. there's a decohering effect of those. Hopefully not a line shift, not one we can think of, but definitely a broadening. Then, damn, what was the second question?
Size of the electron.
Yeah.
Yeah, so, you know, I sort of think of the electron as being a point charge that polarizes the vacuum around it. And what is the vacuum? The vacuum is actually the 0 point of many, many, many particles, including exotic particles with mass 20 TeV. And so surrounding the electron, there's sort of a little haze of particles, and some of those particles are maximally parity violating or time reversal varying. And I have to sort of average over that snowball of stuff. Obviously, if you were a serious particle physicist, you'd be laughing now. But you and I understand each other. Like we can say things like that because we have no illusions of being, you maybe, but not me, as a serious particle physicist.
One more? Or? Yeah, one more if we have one. Maybe can I just ask one quick one? You just said that this molecular ion wasn't chosen for its diagonal Frank-Codden factors necessarily. Thinking ahead, beyond generation 3 of the apparatus, is there thoughts about other ions, multiply charged ions? I don't know. I mean, something that might have the best of many different possible.
Well, there are stories out there of exciting, actually not ions, but exciting polyatomic neutrals, which are relatively easy to, they're very diagonal, therefore laser coolable. You can put them into an optical lattice. Presumably you can pump them to very high contrast. And they're very glamorous stories, right? Work at Caltech, work at Harvard, elsewhere. My impression is that it's a long ways off, but it's definitely, in principle at least, one problem with ions is space charge. We would probably have more ions there, except that the size of our ball of ions is actually space charge limited. It's not the kinetic pressure of the ions, it's their space charge. So we can't really do very many more ions, but if you could have, in principle, 1,000 times more molecules in an optical lattice than Jun-E does, right? So, yeah. And those are designer polyatomic molecules that are designed to solve all your possible problems.
We will hear more about those this week for sure. Well, very good. Let's thank both speakers for 2 terrific talks. And
Thank you.
And a quick announcement from Joseph.
All right, thanks everyone. So even though you haven't been trapping neutral molecules, you might all be tired. And so there are some refreshments available, but not to be had here, to be had at the poster session, which is at Hart House on University of Toronto campus. It's due south from here. Some people know where this is. If you know the campus well enough to know where Hart House is, could you raise your hand? Okay, so follow one of those people. Let me try to quickly tell you what to do, though. Hart House is due south from here, about 8 minutes walk. You want to walk down Philosopher's Walk, the green path to the east of the building. So don't go out the front to Bloor Street. Go down into the atrium and out the side door. So we'll walk down Philosopher's Walk. Then you're over halfway there. Then you need to walk down Tower Road towards the Soldiers Tower, and there you'll enter the west side of Hart House. So if you're Googling this, look for the Soldiers Tower. The front of Hart House is under construction, so you can't just go in the front door, unfortunately. One final note is that it worked really well to have people passing a microphone around, but now we need a whole new set of volunteers to do that. So if you're interested in helping out, please stop by the registration desk, and Glinda will take down your name and give you either a morning and afternoon to help out. So thank you already to Alex and Farzan and the others who were running a microphone today. We'll have more of that in the days to come. Thank you.